In section 6.8, we are going to do a quick review of derivatives and antiderivatives for logarithmic and exponential functions. Most likely you saw this in Calculus 1, but we are going to just do a quick review. This is something that's going to be really important in Chapter 7. So we're going to start with logarithms, and we're not just limiting ourselves to natural logarithms. We're going to look and see what the derivatives and antiderivatives for logs with other bases besides e are as well. So let's start with derivatives. For the basic derivative of just natural log, this is our easiest, and the rest of them are going to be based on this. So the derivative for natural log of x is 1 over x. If we were asked to find a derivative for a log with a different base, so let's say log base 3 of x, there is a formula that you can just remember, but I think it is more worthwhile to see why this formula comes about. In algebra, we learned something called the change of base formula. So we can change this log base 3 of x into a natural log if we set up a quotient with natural log of our input on the top and natural log of our base on the bottom. We really are allowed to change this to any type of log that we want to, but for derivatives here, it's going to be most beneficial to do natural log of x, since we already know the derivative for natural log of x. So natural log of 3 is just a number. It's just a value. It doesn't have any variables in it. You can type natural log of 3 in your calculator. It'll give you back some decimal. So really, we can think of the natural log of 3 as a coefficient. And since it's in the denominator, we would bring it out to the front as a fraction where it stays in the denominator. And then really we're just asking again, what is the natural log of x? Which is what we leave inside. That's the piece that still has the variable in it. And we know from above that the natural log of x is 1 over x. So we get 1 over natural log of 3 times 1 over x, which is easier to just combine into a single fraction. It is typical to have the natural log at the back. That way you don't have to surround the 3 with parentheses. It's just assumed that anything that comes behind it's inside. So 1 over x natural log of 3, which is going to lead us to just a general formula for the derivative of any natural log. So no matter what the base is, you see that all that happened to the 3 here is it ended up as a natural log of 3 in our denominator. So for any log base a of x, the derivative would be x, 1 over x times natural log of a. You also need to keep in mind here all of your special derivative rules from Calculus 1. And that was our product rule, our quotient rule, and our chain rule. The product rule says if we want to take the derivative of 2 functions of x that are being multiplied, so the derivative of f of x times g of x. We can't just take the derivative of each function individually and keep it as a product. What we do is we take the derivatives one at a time. So I'm going to do f prime, and it gets matched up with original g, and then we flip-flop. We do original f times g prime. So we could do some log derivatives that also require us to do a product rule. The quotient rule is similar. We're trying to find the derivative of a fraction that contains two functions of x. So our derivative is going to be a fraction. In the numerator, we have an expression that looks very similar to the product rule, where we start with the derivative of the top and multiply it by the original of the bottom. One big difference, though, is we have subtraction between our two terms in the numerator. And then we flip-flop those derivatives just like we did in product rule. So two main differences. It's subtraction between those two terms, and then it's also all divided by g of x squared. Finally, our chain rule from Calculus 1 tells us how to take derivatives when we have a composite function. So this is when one function is plugged into another function. So you start first with the derivative of the outside function, but you leave the inside alone. And then we'll multiply by the derivative of the inside function. So we could do derivatives of logs that also require us to use these special Calculus 1 rules that we've learned in the past. So just a few quick examples. We're going to calculate each derivative. And the first one that we are going to try is the derivative for x squared times natural log of x. So this function that we were just asked to find the derivative for, x squared natural log of x, we see that it's got x's in there multiple times. So you need to determine what the operations are between those pieces that each have x's. And in this one, it's multiplication. That means we need to use the product rule. So with product rule, we're going to take the derivative of the first piece, which is x squared, so the derivative for that is 2x, and multiply it by the original of our second piece, natural log of x. And then we will flip-flop it. We'll say plus original first and derivative of the second. Remember, the derivative for natural log is 1 over x. And we can clean this up just a little bit. X squared times 1 over x. We can use power rules and just simplify that to a x. For the next one, we want to find the derivative of the natural log of 3x minus 5. This is a composite function because I have a function of x plugged into another function, a natural log. So we start with the derivative rules for the outside piece. And the derivative for any natural log says you take what's inside and you put it in the bottom of a fraction. Just like when we said the derivative for natural log of x is 1 over x. The natural log of 3x minus 5, the derivative starts off with 1 over 3x minus 5. That's just the rule for natural logs. Since this is a composite function, we also have to multiply by the derivative of what's inside, and that's a linear expression, and its derivative is 3. So this is 3 over 3x minus 5. There are quite a few problems where we don't just have a plain old simple linear x inside of our log. So you may have also in the past seen a formula specifically devoted to this type of derivative. So if we want to take the derivative of the natural log of some function, the rule is with that function, its original always goes in the bottom, because that's a rule for taking derivatives of natural logs. And then chain rule says we'd also have to take the derivative of what's inside, and when we do that, it's not going to be in the fraction. So when we end up combining it with the fraction, it goes in the numerator. So you may have seen this formula before. The natural log of g of x, its derivative is g prime of x over g of x. And that's just a consequence of the chain rule. And one more really quickly. The derivative for the, let's do, not natural log, let's do log base 5. Of x cubed. So remember, with log base 5, the only thing different we saw when we worked it out with that change of base formula is that our denominator has an extra ln of 5 at the end. The rule for derivative of logs is whatever's inside the log goes in the denominator, and then chain rule says multiply that by its derivative, which would be the same as putting it in the top. And we can use some operations on exponents there and just simplify this down to 3 over x natural log of 5. If you remember your algebra properties for logarithms, those could be very helpful for some of these problems. So I'm going to review those really quickly. Now these aren't going to ask for any derivatives or antiderivatives. These are just things we learned in pre-calculus algebra. If you have any type of log, it could be log base 5, it could be natural log, it could be our common log, which is log base 10, and inside of that log you are multiplying. You can, if you choose to, split that into 2 separate logs with addition between. And that could make a derivative much, much easier. Instead of having to do a chain rule and then a product rule, if we could get those separated, then it turns into just 2 simple log derivatives. There is a similar property for division. The only thing different is if we're dividing inside of the logs, they would get separated with subtraction. And finally, there is a property for when we have log of some expression to a power. The property says that power can be pulled out front as a coefficient. And that again could avoid potentially like a double embedded chain rule. Now we saw something like this third property back here in this last example where we had the x cubed. So we could have, if we wanted to, pulled that 3 out front as a coefficient, and then we wouldn't have had to do this chain rule where we did derivative of the outside times derivative of the inside, but we would still end up with the same answer. That 3 out front gives us our 3 in the top, and then we just have the derivative for log base 5 of x, which is x ln of 5. So we get the same answer, and possibly a little bit quicker if we apply those algebraic properties of logarithms first. So antiderivatives are just derivatives backwards for the most part. So when we look at antiderivatives here, we're going to be looking at finding the antiderivative of some sort of fraction with a linear denominator, and it's going to turn into a natural log. We wouldn't ever intentionally or purposefully turn these into logs of some other type. All of these antiderivatives will always have an answer of natural log. So the antiderivative for 1 over x with respect to x is natural log of the absolute value of x plus c. Now the absolute value is important because we want to make sure that whatever values can be plugged into that original integrand, we want to make sure those same values can also be plugged into our antiderivative. So the only value right now that we can't plug into 1 over x is 0. X can't be 0. And if you were to just say the antiderivative was natural log of just regular x, well, natural log has a domain of x greater than 0. You can't plug a negative into a natural log, even though a negative would be perfectly fine in the fraction. So what we do to take care of that is we put the absolute values around so that even if a negative were to end up inside, the absolute values would change it back to positive and we would be able to evaluate. Now we don't have to worry about making this work at 0 because the original integrand didn't work at 0 either. So that's perfectly fine. We just want to make sure that the numbers that did work in the original integrand can still work in our antiderivative. And we can see problems like this in lots of different forms. The key usually is to look for a linear denominator. That means a denominator with a power of 1. Sometimes we might see it right away. Sometimes we won't see it until we do a u substitution. Most of these problems are also going to require u substitution. Very rarely will we see just antiderivative of 1 over x. Before we look at that first example, though, you may be tempted to look at that integrand and say, oh, well, I can bring that to the numerator as x to the negative 1 and do the power rule on it. If you try that, remember the rule for antiderivatives with power rule is to add 1 to your new exponent and then take that new exponent and divide by it in front. Well, when you do that operation, you're going to get 1 over 0 x to the 0. X to the 0 is fine, but this 1 over 0 is a big problem. We are not allowed to divide by 0. So if you ever catch yourself doing this, it's okay, because most powers of x we can just use power rule on. This is the only one where we can't. And we realize that once we get this 1 over 0 out in front as our coefficient. That should be the clue in your mind to remind you, oh, this is the one that I can't do power rule with, this is the one that turns into natural log. So this doesn't look exactly the same, but it does have the linear expression in the denominator like I told you to watch out for. When we first reviewed u substitution, remember, we said we could look at that integrand, and if we saw division, multiplication, or composition, that would tell us that we have to use u substitution. So what we have here is a fraction. So a fraction is the outside function, and 2x minus 1 in our denominator is the inside function, because it's just a piece of our integrand. So we need to actually work out a u substitution for this, where u is 2x minus 1. Take the derivative for both sides of the equation. We get du is equal to 2 dx's. And I don't have another 2 in this integral to get rid of, so I'll go ahead and just divide that 2 over, and that's going to put an extra 1/2 into my integrand when I perform this substitution. So this integral turns into the integral of 1 over u times 1/2 du. Now, integral of 1 over u and integral of 1 over x mean the exact same thing. You've got 1 over just a linear variable. So that's going to turn into natural log of u. The 1/2 is just a coefficient. And since we're not evaluating, we say plus c, but you're also, remember, not done until you turn this back into a function of x. So 1/2 natural log of 2x minus 1 plus c. One more real quick, and depending on your Calculus 1 course, you may have had to memorize this antiderivative, but I'm going to show you how we can do it pretty easily with our natural log rule here. If we want the antiderivative for tangent of x with respect to x, remember that tangent is just sine over cosine. And the derivative for sines and cosines, most people don't have a problem remembering those, but once we start doing our other 4 trig functions, they can start to get much more difficult. So once we write the tan as sine over cosine, we see that our integrand has division in it. That means we have to do a u substitution. So even though the derivative for sine is cosine, we rarely ever let u be the numerator. Anytime we decide to do u substitution for a fraction, u is going to be the denominator. And that's because how our derivative, when we take du, comes back into the problem. It comes back in usually as a division. So I don't want to leave my original denominator in there in the hopes of canceling it. It won't cancel when I bring my derivative back in. It's also going to be in the denominator. So if we want to cancel using multiplication, we want common terms in the numerator and the denominator. So I'm going to let u equal cosine. That means du is going to be negative sine x dx, which is perfect because we have sine x dx right there. We just don't have the negative. So I'll divide negative 1 over to the other side and say negative du can replace my sine x dx. And then this integral turns into the sine x dx goes away, just turns into negative du. And then we still have a fraction here. That cosine is still in the denominator. So we do a little placeholder numerator of 1 divided by u. Now that negative is not subtraction. It's like a negative 1 coefficient. And now we're right back to the format we saw in the last one, where the antiderivative for 1 over u is natural log of u. And again, that negative there is a coefficient. And then u was cosine. So our final answer is negative natural log of the absolute value of cosine x plus c. So just to recap really quick, the derivative for natural log of x is 1 over x. If you're doing any other type of log, you could use your change of base formula to change it to a natural log, but really all that's going to do is it's going to put natural log of your base as an extra factor in the denominator. These derivative problems are not always going to be simple and straightforward. You may have to combine product rule, quotient rule, and chain rule. And we did a couple quick examples of that, a product rule and a chain rule. It's very common to see chain rule with logs. So from Calculus 1, you may have also seen this formula for derivative of log of g of x. And that is just, that's just a result of chain rule. And then we did one with a different base. Remember, these properties of logs can simplify your function immensely, and you are allowed to apply them before you do your derivative, and they can make your derivative much, much easier. And then finally, our antiderivative is just our derivative in reverse. So this time we start with the derivative of 1 over x, and we want to go backwards to the original function. The one trick here is that you have to have those absolute values around, and that's because we want the domains for those two functions to match. And usually these problems are going to require u substitution. So we did a couple quick examples and showed how that u substitution will work to get us an answer that includes a natural log.